Have you ever wanted to build your very own deep image classifier? Well, in this tutorial, we're going to do exactly that. Let's do it. What's happening, guys? My name is Perofmrnace, and in this tutorial, as I mentioned, we're going to be building a custom deep image classifier using your own data. Now, the nice thing about this tutorial is that you can literally pull down any bunch of images from the web and load it into this pipeline, and you'll be able to use it to classify images as a 0 or 1 binary classification type problem. Now, in this tutorial, we are going to be very much focused on going through the end-to-end pipeline. So first up, what we're going to do is focus on getting some data and loading it into our pipeline. We're then going to take a look at some pre-processing steps that we need to perform in order to improve how well our model performs. Then we're going to build our deep image classifier using Keras and Tensorflow. So we'll build a sequential deep neural network. Then we'll evaluate it, test it, and last but not least, we'll save down this model so that you can take it elsewhere and use it where you need it. Ready to do it? Let's get to it. Hey Nick, I was hoping to build a deep learning model to classify some pictures. Is that something that's possible? What are you trying to classify? It's part of my stealth tech startup. We're looking to build a cutting edge mobile app that classify YouTuber thumbnails as, wait for it, shocked face or duck face. I'm gonna need you to sign an NDA now that you know that. So you like the idea? Right. Well, my other idea is to use AI to classify images of people as happy or sad. Okay, that we can do. We can use image classification to do it. Nice, how do you get started? Well, the first thing we probably need is to get some images of happy and sad people, then we can use some of the helpers inside of Keras and TensorFlow to load it up. So we doing this or what? Yeah, let's go.
Alrighty guys, so we are going to be going through an end-to-end image classification deep learning pipeline thing. Wow, that got really long really quick. No, so we are going to be able to build our very own deep image classifier using pretty much whatever data you want in this particular tutorial. This is sort of why I wanted to show you this. So first things first, what we're going to need to go on ahead and do, and this is what we discussed with our client, is we need to go and set up and load some data. And then in order to do that, we are going to do a couple of key things. First up, we're going to install our dependencies and set them up. We are also going to remove any dodgy images. So I found that sometimes when you download images from the web, i.e. images versus images that you haven't captured yourself, you can tend to get some dodgy images or images that are corrupt. So I'm going to show you how to remove those. We are then going to load that data. So those are the first couple of things that we need to do. So first up, installing dependencies and setup. And as per usual, all the code that you see inside of this, including the entire Jupyter notebook, is going to be available inside of GitHub. Just check the link in the description below. So first things first, we need to install dependencies and setup. So what we can do in order to do that is run this particular line here. So the first line is !pip install TensorFlow, TensorFlow GPU, OpenCV-Python, and Matplotlib. So TensorFlow and TensorFlow GPU are going to be used as part of the deep learning pipeline itself. So we are going to use the Keras sequential API in a second to be able to go on ahead and do that. OpenCV is going to be used when we go and remove our dodgy images, and Matplotlib is going to be used to visualize our images. So if we go and run that, that is going to go on ahead and install our dependencies. So we scroll on down. Looks like we just got a warning, and this is just telling us that we should probably update our pip version, but in this particular case, it's fine. We don't need to. Cool. Then we can go and validate whether or not we've got the right dependencies installed. So if we go and run pip list, let's go and take a look. So do we have TensorFlow? So we've got TensorFlow and TensorFlow GPU. So we've got 2.8.0 and 2.8.0. If you haven't watched the beginner setup tutorial, which I just released, make sure you go and visit that, particularly if you've got a GPU and you need to set up TensorFlow with GPU acceleration. I go through it step by step, so it's going to make your life a ton easier. Okay, so the next thing that we need to go on ahead and do is import some dependencies. So in order to do that, we're going to import two key dependencies. The first one is TensorFlow. So import TensorFlow as TF. And the second one is OS. So we've written import OS. So OS is namely used, let me minimize that. So OS is mainly used to navigate through file structures. So typically when I'm using OS, I'm using it for os.path.join. So let's say, for example, we need to go into our data directory and we needed to go into a folder called happy, right? So what this is going to do is return back a file structure, which is, homogeneous regardless of what type of operating system you're using. So this is, if you're using it on a Windows machine, it's going to be perfectly fine. If you're using it on a Mac or a Linux machine, it's going to return the folder structure in a format which is appropriate for that particular type of operating system. Now, the other main type of function that I use inside of OS is os.listdir. So let's say, for example, I wanted to show all of the files or all of the images inside of a particular directory. I could actually type in os.listdir, and let's say I got a folder called data. It's going to list everything that is inside of that particular folder. Now, I don't have anything in there, but later on, you'll actually see that in use. Just a couple of key tips on what I use OS for. All right, next line, we are going to go on ahead and limit TensorFlow using up all of the VRAM on our GPU. So by default, when you load in TensorFlow or you load in data, it's going to expand and use all of the potential VRAM that's available on your machine, which tends to become a bit of a nightmare, particularly if you're getting into really big models. So these two particular lines of code actually help prevent that. And it helps prevent something called an OOM error, or an out of memory error. So first thing that we're doing is we're actually grabbing all of the GPUs available on our machine. So the first line is GPUs equals tf.config.experimental.list_physical_devices. And to that, we've passed through GPU, right? So if I actually go and write that line, so GPUs equals tf.config.experimental.list_physical. Oh gosh, my typing is a shocker. Devices. And then if I type in GPU, this is going to give us all of the GPUs that we've got available, right? So you can see I've got one there. If I had a giant machine that had multiple GPUs, you'd actually see multiple there. So if I take a look at the length of that particular line, you can see we've only got one GPU available there. We typed in CPU, you can see, again, I've only got one CPU available, right? So in this particular case, it's returning my CPU. So if you wanted to see all the devices you've got available, you can filter through on that. So that is what that line is doing there. Then the next line is actually limiting the memory growth. So we're looping through every potential GPU that we've got inside of this line here. So for GPU in GPU, so for each of the GPUs inside of this, we are going to run tf.config.experimental.set_memory growth. So this is telling TensorFlow, hey, don't use up all of our memory, keep it to a minimum or keep it to whatever you absolutely need. So by limiting this, it ensures that we're going to avoid any of those out of memory errors. You might still get some if you've got batch sizes that are too large, but that is a solvable error. Cool. So we have now gone and installed some dependencies, imported a couple, and we've also gone and limited our memory growth. This next line is just showing you exactly what I showed there, so you don't need to run that. But if we go and run that, that is going to limit our memory growth. So you saw that it wasn't run there. I've just gone and run it. So we are now good. So that is step 1.1 now done. So we've gone and installed our dependencies. We've gone and imported whatever we need. And we've also gone and limited our memory growth over here. Now, the next bit is removing dodgy images. Now, before we actually do that, we actually need to get some images. So the nice thing about this tutorial is that I wanted to build it so that you could actually go and build an image classifier for just about anything you wanted. Now, the nice thing about this is that we can actually go and get a bunch of images from the World Wide Web. So we're going to be building an image classifier, or an image sentiment classifier in that particular sense. So what do we need to do? We need to get some images of happy people. So let's get images of happy people. So I'm just going to go to Google, go to images and type in happy people. And you can see we've got a bunch of overly ecstatic people over here. They're so happy. Who knows what about? We're going to go on ahead and download these. Now, I've actually got this extension inside of Google Chrome, which makes my life a ton easier when it comes to this. I don't actually know. What's it called? More tools, extensions. It's this one over here, download all images. So if you go and get that particular extension, this is going to be a game changer when it comes to building deep learning stuff, right? Because what we can do is from here, I can open up this extension. So you can see it says download all images there. Yeah, I can click that and that is going to start downloading all of the images from this page. So you saw it just literally went and did that. So inside of this zip folder, we got all those images. So if I go to downloads, open this up, take a look at that. Images of happy people. How cool is that? Pretty awesome, right? So we're now able to build up a deep learning image data set really, really quickly. So we're going to grab that particular zip file. So I'm just going to cut that and I'm going to take it into my image classification repository. So I haven't actually shown you this let's do that. So this particular notebook is here, and inside of this same folder, I've got a directory called data, a directory called image classification, which is just my virtual environment. Again, if you haven't seen the beginner tutorial, go and jump back on over to that because I show you how to set this up. Got a folder called logs because that's where we're going to log stuff out. We've got a folder called models as well. Now, we are going to grab this data that we just downloaded and put it into our data folder. And I'm just going to rename it and call it happy. Just double check that is the right thing. Yeah, that's cool. Happy people. So happy. All right, so we are going to go, what have we gone and done? So we've got a set of image data, which is for happy people. We now need a set of data, which is for sad people, kind of like when I don't get to order pizza or beer on Friday night. So we've got a bunch of people that are sad. So again, we're going to go to our extensions, download those images. So you can see it's downloading. We're good, we're great. That is now downloaded over there. So again, we're going to go to our downloads. We're going to grab that repository, paste it over here, and we're going to call this one a sad. So we've now got inside of our data folder, we've got two zips. So we've got a happy zip, we've got a sad zip. So we're going to extract these now. So if we go and extract these, and we're just going to create or extract them to a separate folder. So we're going to extract to happy. Let me zoom in because that's way too small. Happy, we're going to extract to happy. I know sometimes my code is pretty small, guys. I work to improve it, I promise. So we're going to extract to happy. You can see we've now got a folder called happy with all of our overly happy people. Right, cool. We're going to go and do the same for sad. And this is gone. What's that pop up? This is saying the following imp file already exists. Let's just say yes to all. Okay, so we've now got two folders. We've got a whole bunch of happy people. Yeah, cool, great. Now, inside of our sad folder, we've got a whole bunch of sad people. This guy's clearly had a big day at work. This guy has as well. All right. So what we're going to go ahead and do is, what are we doing? So we're going to take these zip folders and we're actually going to move them back into this root folder. So that way they don't sort of mess around. Because when we go and load in our data, the Keras utility is just going to look at the subfolders that it needs in here. Cool, so I'm going to close that, I'm going to close that, I'm going to close, wow, I've opened up a ton of images. We don't need that one open either. All right, cool. So what have we gone and done? So we've gone and downloaded a bunch of images, sad people, a bunch of images, happy people, and we've now gone and put it inside of our data folder. If you wanted more classes, you literally just go and download those classes, paste them in here. You do need to change the neural network a little bit. If you want a tutorial on that, hit me up in the comments below and maybe we'll make one. Okay, so we've gone and got our image data sets. We've got one of happy, one of sad. Now we are kind of goodish to go. So the next thing that we're going to do is we're going to go and remove dodgy images. Now, let me explain why we're doing this. So sometimes when you go and get images from the World Wide Web, even though they have the appropriate file extensions, they might not open up in Python because they might be corrupted, they might be mislabeled, they might be misextended or have the incorrect extension applied. This particular block is going to help us get rid of that. So first thing that we need to do is import two dependencies. So we are importing OpenCV. So this is what allows us, let me actually show you. So if we type in OpenCV, it's a huge OpenC or Open Computer Vision module that allows you to do a ton of computer vision and good stuff. So this is super awesome. If you've never checked out OpenCV, by all means do. The next thing that we are importing is image HDR. So this allows us to check the file extensions for our particular images. So two lines there. So import OpenCV and import image HDR. The next thing that we're going to do is create a variable to hold the path to our data directory. So remember, inside of here, we've got a data directory, which is called data. And inside of our data directory, we've got two folders, one called happy and one called sad, right? So we're going to go and create a variable which points to that. So data underscore dir equals data. Then we are going to go and create a list of extensions. Let me minimize that. We're not talking about that yet. Too early. So our image extensions are JPEG, JPG, BMP, and PNG. So this is just a standard list. So if we go and navigate through this, let's actually run that first. So image underscore EXTS, right? I haven't typed that in. IMAGE. Right, it's literally just a list. So if we actually go and grab the first one, That's JPEG. The second one, that's JPG. The third one is going to be PNG. That's actually the fourth one. Cool. So the reason that we're setting up this is we are now going to loop into it. So remember how I told you about import OS? So now what we can actually go on ahead and do, let's check this out. So if I type in os.listDir and type pass through data dir, this should return happy and sad. It returns the folders which are inside of this data directory. If I go and run that, happy and sad. Pretty cool, right? Now, what would happen if I wanted to go and check every single image inside of the happy folder? Well, I could go os.path.join, pass through my data directory, and then pass through, let's say, for example, our happy folder. Now, I'm going to return every single image inside of that subfolder. Pretty cool, right? So this allows us to loop through every single image that we've got inside of that folder, which is exactly what our dodgy image script is going to do in a second. But I just remembered there's one additional thing that we need to go on ahead and do. So before we actually go and run that image script, normally what I'll do when I'm getting images from the interwebs is I'll actually go into that data set and just anything that is small or weird, I'm going to remove that. So anything which is under 10 kilobytes, which is probably going to be a really small image, and all of these weird Microsoft Edge vectors, we're going to get rid of those. So from 9 kilobytes onwards, so you can see, let me zoom in. So you can see these are 9 kilobytes, 8, 4, 3, so pretty small. We're going to get rid of those. So from here to here, delete those. And if you wanted to add in additional images, so go and do like go to another page, download more, go to another page, download more, you could definitely do that. Okay, so we've gone and removed the small and weird images from happy. Let's go and do the same from sad. Let's go to our details tab. So again, we're going to find 10 KB and then we're going to delete everything below that. You can see 9, we're going to go all the way down. We're going to remove anything smaller than that. Got to get rid of that quick assist. It's driving me insane. All right, so down here. Let's take a look. 9 kilobytes, 1 kilobyte, remove those. Boom, done. All right, cool. So that leaves what effectively should work. But we're still going to run our dodgy image script as well, just to make sure that we don't have any weird stuff there. So remember how I said or talked about os.listDir? That's exactly what we're doing. So first up, we're looping through every folder that we've got inside of our data directory. So for image class inside of os.listDir. So this is just going to go inside of our data directory and it should effectively just print out happy and sad. So if let's actually show you this, or let me actually show you this. So print image class, image, image underscore class. So we're going to print out happy and we're going to print out sad. Then what we're going to go on ahead and do is we're going to print out every single image inside of those subdirectories. So if we go and print that, so if I go and print image, we are printing out or looping through every single image. And then we're just going to do a bunch of checks, right? So if you wanted to do a specific check, you could go and do that. I'm just double checking that 1, we can load the image into OpenCV, and 2, that our image matches one of these paths over here. So if we've loaded it up and it's still weird, we're actually going to remove it from that particular folder. Right, so what we're doing is for looping through every single one of our data directory folders, so happy and sad, we're then looping through every single image that we've got inside of those subdirectories. So in order to do that, we're in for image underscore class in os.listDir, for image.os, or for image in os.listDir, and then we're going into those subfolders. So we're joining the path. So os.path.join our data directory, and then our image class. So this would effectively be happy, and then, well, no, this would be data, and then it will be happy, and then it will be data, and then it will be sad. And then we're going into that and we're grabbing every single image explicitly. So we're going os.path.join, the data directory, the image classification folder, and then the image itself. And we're storing that inside of a variable called image path. And then we're passing that through to opencv.imread. So this actually opens up an image, or it allows you to open up an image using OpenCV. So let's actually test that out, right? So if I type in cv2.imread, and then we need to pass through the full file path. So we're going to pass in os.path.join because it just makes it easier. We're then going to pass through our data folder, and then let's say, for example, happy, and then let's go and get a file from happy. So I go to image classification and then data, happy. Let's grab this one. Looks pretty big. And we're going to pass through the string. So there's a JPG, so we need the extension as well. The image classification, data, happy, it's JPG, cool. .jpg. We need to close that. So you can see we've just gone and read in our image as a NumPy array. So if I type in, let's just store it inside a variable so I can show you. Type image, it's a NumPy array. Now what does this actually mean? So basically, let's take a look at the shape. So we have an image of the shape, what is that? 3, so this should be rows first. So it's going to be 3,744 pixels high, 5,616 pixels wide, and it's got 3 channels. That means it's a colored image. So if we actually go and open up that image, so well, let's actually use our Python capability. So we can type in plot.imshow and then pass through our image. And have we not imported matplotlib? We have not. Let's import matplotlib. Let's just import up here. So let's just add in another line. So we're probably going to visualize it later, but I want to show you now. So from matplotlib, import pyplot as plt. Let's go and run this. So that is our image there. So you can see 744 pixels high, 5,616 pixels wide, and it is a colored image. Now you're probably wondering, Nick, why is it a weird color? This is because OpenCV reads in an image as BGR. Matplotlib expects it to be RGB. So if we wanted to fix this, we can type in cv2.cvt color, pass through the image, and then pass through a color conversion code. So this is just going to reorder the channels. So we can type in cv2.color _ BGR to RGB. Boom. Yep, that should work. And there you go. So you can see the colors now fixed. And we can, if we wanted to get rid of this weird line here, you can just type in plot.show. Look at that. So pretty. So again, so this particular line effectively shows you, one, how you can read an image using OpenCV, how you can join paths using os.path.join, and how we can go and render those. Okay, but this was just sort of explaining. So we don't need this, we don't need this, we don't need this, we don't need this, and we don't need that. What we want to do is actually go and run through our dodgy image script. So again, if it's not a valid image, not a valid image extension, we're going to go and get rid of it using os.remove. So os.remove allows you to delete a file. So let's go and run this. And you can see that this is inside of a try except block. So effectively, if it throws up any errors, then we're going to fail out of that particular block. So let's go and run that. See, we've got some weird images. It's removing them. And that is done. So now let's just double check we still have a bunch of images inside of our data folders. So if we go into data, happy, still got a bunch of images there. So 131 to be exact. And inside of SAD, we've got 74. So it looks like it's a bit of an unbalanced data set. So we could definitely fix this up or resample if we needed to. But for now, we'll be okay. Cool. So we've got a bunch of images. We've gone and cleaned them up. We're looking good. So let's take a look at what we've done so far. So we've now installed our dependencies successfully. We've also removed any dodgy images. The next thing that we want to go on ahead and do is load our data. Now, how are we going to do this? Well, TensorFlow actually has a dataset API. And I originally didn't use this a ton when I was just getting started on my deep learning journey, but now I probably use it every single time I'm building a deep learning model. Why? Well, it actually allows you to build data pipelines. So rather than loading everything into memory to begin with, it actually allows you to build a data pipeline, which one allows you to scale out to much larger data sets, but it also gives you a repeatable set of steps that you're going to apply to your data. To be honest, just makes stuff a lot cleaner. There's a whole bunch of documentation on this. Now, if you wanted to actually access it, you can type in tf.data.dataset, and it actually allows you to access this tf.dataset API. Now, we're actually going to use it slightly differently. So rather than using the dataset API directly, we're actually going to use a Keras utility, which actually allows you to do it. But for example, if you've, in some of the tutorials that I've actually got coming up, namely iris tracking and which other one did I use it in? I think for the toxic comment detection, I actually use it. So typically you can load in a data set using tf.data.dataset from, from tensors, from generator, from tensor slices. But you can also use it and load in data from a directory by typing in list files. So this actually allows you to do a wildcard search. So I just wanted to give you a little bit of background on this, but we're not going to be using it directly in this particular tutorial, but there is a ton of capability in this TF dataset API. Okay, that is the dataset API talked about. Now, we've also taken a look at its documentation. So also pro tip, if you've haven't used Jupyter too much, if you type in question mark, gives you the documentation for that particular line of code or that method, which you can see there. So next thing so we're importing matplotlib there. So I re-imported it up here, but I wanted to show you that image visualization. So we are now importing NumPy. So import NumPy as NP, and then from matplotlib, import pyplot as PLT. So if we go and run that now, that's 2 new dependencies imported. And then this is where we're going to load our data. So remember how I told you that we've got this dataset API here. Well, Keras actually has a data pipeline or function or helper built into it as well. And this is how we access it. So in order to use it, you can type in tf.keras.utils.image_dataset_from_directory. And this actually builds an image data set for you on the fly. So you don't need to build the labels. You don't need to actually build the classes. It's going to do it for you. And it's actually going to do a bunch of pre-processing out of the box. So it'll resize your images as well. Now, let's actually take a look at the doco for that. Nope, we don't want to take a look at that yet. So if we go to tf.keras.utils, utils.image. So it is actually going to batch your images into a batch of 32. It's going to resize your images into 256 by 256. It's going to shuffle them. You can also create a validation split, so on and so forth. But it's pretty cool, right? So it actually allows you to do a ton of stuff right off the bat. So this is a super useful helper if you're building image classification models. So we're going to get rid of that. So we're actually going to create this data set now. So I've just gone and run this line here. So we are then going to store our data set into a folder or into a variable called data. So this means that we can now take a look at the data itself. Now, the nice thing about the data actually, it's nice, but it's also a little bit painful. So let's say, for example, I wanted to go and take a look at this data. I can't just go and grab the first instance because this isn't a data set which is preloaded into memory already. It is actually a generator. So on the fly, we actually need to go and grab the data that we want. Now, the easiest way to do that is to convert it into a NumPy iterator first, which is what this next line is doing. So we are going to go and create a data iterator. So data_iterator equals data.asNumPy iterator. So you probably would have seen me do this before in the face verification tutorial. I actually did it there. So this is going to convert or allow us to access the generator from our data pipeline. So data_iterator equals data.asNumPy iterator. Then we can actually get consecutive batches using the .next method. So I'll show you this in a sec. So if we go and run that now, then our next line of code is actually going to run .next. So this is actually going to get us a batch back. But first up, let's take a look at our data iterator. So you can actually see it is an iterator, so also like a generator, so you can loop through and continuously pull data batches back, right? And again, this is probably not hyper useful right now, but when you get to significantly more sophisticated deep learning models where you got massive amounts of data, going to make your life a ton easier. But for now, let's actually take a look. So we are then going to grab one batch. So if you think about it this way, so this is building our data pipeline. This is actually allowing us to access our data pipeline, and then this is actually accessing the data pipeline itself. So this is allowing us to loop through it. This is grabbing one batch back. So if I go and run this line, this batch, let's actually take a look at the batch before we visualize it. So if I type in batch, so this is actually a batch of data. So this should have a shape of 2, or it should have 2 variables or 2 parts to the tuple. Now, you're probably thinking, Nick, what the hell is this number 2? Well, there's 2 parts to this data set. There is the images and then there's the labels. So the first part is actually the image representation. So it's our images from our directory loaded into memory as a set of NumPy arrays. So if I go and grab that first value, we've got a whole bunch of arrays here. Yeah, can you see that? Now, if we take a look at the shape, we should have all of our images loaded. So if I type in .shape, so we've got a batch size of 32. And remember, this is based on the image_dataset_from_directory helper method. We can configure that if we wanted more images per batch or if we actually wanted different image shapes. But this is the nice thing about that particular utility. It automatically reshapes our images to ensure that they are of a consistent size, and it also batches them up into a batch size of 32. But again, you can configure all of this. So let's say, for example, let's actually go and grab it. So tf.keras.utils.image dataset from directory. So if I wanted more images per batch, I can increase that. Let's say, for example, you don't have as much VRAM on your GPU. You could actually drop that batch size. And the way that you would do this is, let's say that that's your data directory. You would type in batch underscore size equals, I don't know, 16, for example, here. Or you'd go batch size equals 8. So you can change that. If you wanted your image size to be different, you could actually pass through that keyword argument. So image underscore size equals, I don't know, let's say 128 by 128. So it would actually allow you to configure what you want your data set to look like. For now, the defaults are going to work. Cool. All right. So we're taking a look at our batch. So we took a look. So these are the images, right? So this is the images. Images represented as NumPy arrays. Now, let's say, what about the labels? So if we go to batch 1, this should be the labels. There you go. So in this particular case, we've got a flag of 1, we've got a flag of 0, 0, 0, 0, 1, 1, 1. Now, these actually represent the labels. So 1 is going to represent either happy or sad, and 0 is going to represent either happy or sad. I couldn't quite work out whether or not there's a way to dictate which class belongs to which number. Now, I know there is a way, I think there is a way that you can actually configure this. I know for sure that you can do it using the tf.data.dataset API because I do it a ton. With this default helper, I'm not too sure actually how you actually go about configuring that. But there's one easy way around that. You just double check which class is assigned to which type of image. And this is what this plot is going to allow you to do here. So over here, we can see that the 1 flag is actually assigned to sad images and the 0 flag is assigned to happy images. So you can see 1 there, 1 sad person, 0 happy people, 0 happy people, 0 happy people. Now, let's say, for example, we wanted to visualize another batch of data. Well, we can actually go and run this line over here again because we are going to get another batch from the iterator. So if we go and run this, again, our batch size is not going to change, but our classes. So you should see these numbers change over here, right? So if we go and run this again, you can see that we've now got a new batch of data from our data pipeline. And just for our own purposes, let's write a note. So class 1 equals sad people. And then class 0 equals happy people. And if we go and run our visualization again, you're going to see that. So 0, happy people 1, sad people 1, sad people 1, sad people. Who is that? Is that Timberland? Kid Cudi? I don't know. But over here, what we're doing is we're actually using matplotlib and matplotlib's subplots function to be able to plot out 4 images at a particular time. Cool, but that is our data set now brought in. So we've actually got that now read in. Let's quickly review what we've done. So we have successfully installed a bunch of dependencies and set them up. We've removed any dodgy images we might have, and we've also gone and loaded up our data using the Keras image dataset from directory helper. Let's jump back on over and have a chat to our client and see what's next.
All right, so now that we got some data loaded, what's next? We got to get pre-processing. What? Pre-processing. For image data, we tend to pre-process by scaling the image values to between 0 and 1 instead of 0 to 255. This helps our deep learning model generalize faster and produces better results. Cool. Anything else we got to do? Yep, we're also going to split up our data into training, testing, and validation partitions to ensure that we don't overfit. Let's get to it.
And we are back. So now what we're on to doing is pre-processing our data. So we've got our data loaded, but now we've got to do some pre-processing. And this is where step 2 comes in. So there's 2 things that we're going to do here. We are going to scale our data. And by that, what I mean is that when we loaded in our data over here, actually, let me show you. So if we actually go to our data, so if I type in batch, and remember our batch is composed of 2 parts, our images and our labels. So our images are going to be in key 0. And our labels are going to be in key 1. If we go to, or index 1, whatever you want to call it, if we go to the first thing, then this is going to be our images. So if we type in .shape, all of our images, right? So we've got 32 images of shape 256 by 256 by 3 channels. Now, when you load in an image is a representation of a number of channels, which are going to be RGB. For OpenCV, it's going to be BGR. When you use TensorFlow, I think it's RGB. but it's going to be of the values 0 to 255. So if I type in .min, does that work? Yep. So this means our lowest value is 0.0 and .max should return 255. Now, when you're building deep learning models, ideally you want the values to be as small as possible. This is going to help you optimize a ton faster. So what we can do is really quickly is all we really need to do is divide these values by 255. And that is going to give us values between 0 and 1 now. So if I type in, so let's say scaled. So if I type in scaled, and then we type in .min. So the lowest value is still 0, the maximum value, now 1. So this means that we've successfully scaled our data. But remember that we are using a data pipeline. So we can't necessarily go and do this every single time we load up a batch. What we want to do in order to do it most efficiently is just do it as we're loading in the data through the data pipeline, using the data pipeline capability. So let's actually go and take a look at how we might do this. Inside of the data pipeline, we've actually got a function called map, and this allows us to apply a particular type of transformation as our data is being pre-processed through the data pipeline. Now, this means that when we go and pre-fetch data, it's going to do that transformation as well. So this means that it speeds up how quickly we can access our data from our disk. So what we've gone and written is data equals data.map. This is really, really important, guys. Pay attention. So data.map actually allows you to perform that transformation in pipeline. So data.map, and then we're using a Lambda function to be able to go and do that transformation. So when we go and access our batch, remember we're going to get our images and our labels. So X is going to represent our images because those are our, our independent features. So we are going to be passing those in. Y is going to be our target variable. So that is what you can see there, or effectively our labels. What we're going to do is that as we load in a batch, we are going to go and get our data over here. So you can see we've got X and we're going to divide it by 255. That is our scaling. And we are going to perform no transformation on our Y. So if we go and run that, we've now effectively applied that transformation step on our data pipeline. Now, there are a ton of additional transformations you can do inside of a data pipeline or a TensorFlow dataset pipeline, right? And if you just go to TensorFlow dataset API, no, TensorFlow data API. Yeah, tf.data. Right, there are a ton of functions. So if I go to tf.data, where is it? Here, over here. So tf.data.dataset, there are a ton of functions. So over here, you can see that there are an absolute ton. So we are using the map function, which you can see there. And again, this allows you to do a whole bunch of stuff across elements within a dataset. Exactly what it's saying there. There's a whole bunch of other ways that you can use it. We're using it in this particular manner over here. Cool? Cool. The other ones that I tend to use a ton are zip. So let's say, for example, I wanted to combine a set of features and labels. Zip, oh, sorry, just slapped the mic. Zip is a way to combine those. Skip, you'll probably see that in a second. What's another one? From generator, tensor slices from tensors. These are pretty common as well, but I'll include a link to this inside of the description below so you can see it as well. But that is effectively our data scaled, right? So now, if we go and take a look at our next batch, you can see that we are doing that inside of our data pipeline. So this is no different to what we did from up here. So rather than going and creating separate variables from our iterator, we can actually access our data like that as well. So data dot and then dot as numpy iterator. So that gives us access to our iterator, and then dot next is going to grab our next batch. Now keep in mind, this is going to, if we're not applying shuffling, it's going to return back the exact same values each and every time. In this case, we've got shuffling. So you can see that our data is changing. Let's just grab our first set of our images. So again, we can grab our images by grabbing the first index. If we type in .max, you can see them. Wait, hold on. That is a very low max. .min, 0, .max, 0.03. That seems very low. Let's grab another batch. So we can, let's call this scaled equals scaled iterator. Data.as numpy array. And then if we go scaled iterator dot next, these all look awfully low. Maybe we've just got images which aren't all that bright or aren't that colorful. Let's go .max. We need to grab our first value again. Grab a next batch. Seems awfully low. Let's actually take a look at it using our plotting function over here. So if we grab that, so let's grab a batch. So that's our data. Then we can grab the iterator, and then let's just create a batch here. Kind of weird that they're so low. Batch equals scale data.next. All right, so data equals that. This is going to be our scaled iterator. Grab a next batch. What does this look like? They're all black. Something has gone wrong there. Let's go and reload our data. So grab our data set. Can skip that bit. Let's go and run through that pipeline. Wait, hold up. So because we've gone and divided our images by 255, they're no longer going to be integers. But right over here inside of our visualization function, we are converting them to integers. But in this particular case, they'd all be 0 because they're between 0 and 1. So if I divide this, this is now on a set of our scale data, right? So data has now got our lambda function. Let's just go and reload our data over here. This is reestablishing our data pipeline. We're then going and running it through our lambda. Then if we go and take our next batch, let's go through our scale data set. This is going to be our scale data. Perfect. So if we go and type .as type int, right, that's going to turn them all black. No go. Colored. Let's just double check. So batch. Okay, so that looks a little bit better now. Hold on. So if we go batch 0 dot max, okay, 1 dot min. I don't know what's happening there, but that looks like it's okay. Good thing that we're double checking that this data is appropriately functioned. Maybe we went and ran that data pipeline twice, so we were going and dividing by 255 twice. That's the only thing that I can think of there. But if we go and reload or reestablish our data set by going and running this line over here, and then if we go and apply our lambda again, go and test this out. Right, so our max is 1, our min is 0. Now if we go and visualize, perfect. All right, cool. So that is our data now scaled. So we know that our images are now between 0 and 1. The next thing that we want to go on ahead and do is split our data into a training and testing partition. This means that when it comes to actually going and validating our data and ensuring that our model hasn't overfit, we've actually got specific partitions. So in order to do this, we are first up going to establish what our training data sizes should be. So let's just quickly take a look at the length of our data in its entirety. So we have 7 batches, and remember each batch is going to have 32 images. So, or there's probably one that's going to be truncated if it's not equal batches, but that is the number of batches that we've got. So our training set is going to be 70% of that data. So that should be what, 49. So it would be like what, 5 batches, so 7 times 0.7, right? So we'll have roughly 5 batches there. Then we're going to have 20% assigned to validation, so that'll probably be 1, and then this will probably be 1 as well. Let's just see what this comes out as. So how big is our training size? 4, so it's rounded down. How big is our validation size? 1, and how big is our test size? 0. So, all right, so we should probably add 1 to that. So that means we'll have 4 plus 1 plus 1. That's only going to give us 6. So let's add an additional one to our validation partition. So train is going to now be 4 batches. Validation is now going to be 2 batches, and test is now going to be 1 batch. So train plus, or train size plus val size plus test size equals 7, which equals this, right? So we're good to go. Now, let me quickly explain what we're doing here. So our training data is going to be what is used to actually train our deep learning model. Our validation data is going to be what we use to evaluate our model while we're training. So this means that our model hasn't necessarily seen our validation partition, but we're using it to fine tune how we actually build this deep learning model. And it's good practice to have a training and validation partition as you're building up these models. Your test partition, your model is not going to have seen until we get to the final evaluation state. So we hold that out all the way until the end. So these two are used during training. This one is used post-training to do the evaluation. And right now, all we're establishing is how much data we're going to allocate to each one of these partitions. So we are going to have 7 multiplied by 32 image, or wait, hold on. We're going to have 4 multiplied by 32 images allocated to our training partition. We're going to have 2 multiplied by 32 images allocated to our validation partition, and we're going to have 1 batch assigned to our test size. Now, we don't need to take a look at that. In order to do this, we actually can use the take and skip methods available inside of the TensorFlow dataset pipeline. So if I actually show you this, so over here, you can see we've got take and skip. So take defines how much data we are going to take in that particular partition. So if we go and run this line here, so our training size, so our len is 4 batches, our val data is 2 batches, and our test data is 1 batch. So in order to do this, first up what we're doing is we're saying train equals data.take, and then we're saying how many batches we want to allocate to our training data. Now keep in mind, our data is already shuffled. If your data hadn't been shuffled, you want to shuffle it before you do this. So train is going to equal 4 batches. So train equals data.take, and then to that we're passing through train size. Val is going to equal data.skip. So first up what we're going to do is we're going to skip the batches that we've already allocated to our training partition, and then we're going to take the last 2 into our val data. So data.skip, and we're going to skip the first 4, which we've allocated to train, and then we're going to take 2 based on the val size. So take 2, and then we are going to take 2 batches, and that is what our validation partition is going to look like. Then our test is going to be everything left over, right? So test equals data.skip, and we're going to skip the training data and the validation data, and then we're going to take the rest, which should be our test partition. And that is how you establish your train, test, and validation partitions. And that is the last step in our pre-processing stage as well. So we've now gone and scaled our data, and I sort of showed you how to actually go and apply that lambda layer or the map layer. And we also saw that we had a bit of an issue there, right? So we saw that our data wasn't necessarily scaled, and this is potentially because we went and applied this twice. Now, in order to fix that, all you need to do is go and rerun this line over here and go and rerun this particular line here. And again, we're overriding variables. So again, that can be a little bit sketchy in terms of how we can actually trace that back. So you might actually go and choose to call this scaled data. So that way you can't override it twice. But in this case, we are good. So our data is scaled. Our data is now between 0 and 255. We've gone and taken a look and visualized it. And we have also gone and created our train, validation, and testing partitions. Let's jump back on over to our client.
Alrighty, on to the good bit. Now that our data's pre-processed, we can begin modeling. I've always told my mom I was destined for the catwalk. What? Yeah. What we're going to do now is build our deep learning model using the Keras sequential API. Nice, so this is the AI bit, right? Right, come on Giselle, let's do this.
All right, so we are now on to the good bit, actually doing the deep learning. So in terms of doing this, there are going to be 3 components. So first up, we are going to build our deep neural network. And in order to do that, we're probably going to need to import a bunch of stuff. Then we're actually going to go on ahead and train the specific deep learning model. In order to do this, we can actually use the .fit method. And then we're also going to plot our performance using matplotlib as well. Okay, so first things first, let's go and import some dependencies using TensorFlow. So first up, what we're going to be doing is we are going to be importing the sequential API. So in order to do that, we've written from tensorflow.keras.models import sequential. Now, the reason that I make this distinction is that there are 2 really specific models, or 2 specific like model building APIs available inside of TensorFlow and Keras. The first one is called sequential, and that's what we're going to be using. This is great if you've got 1 data input and 1 data output, and the model sort of just flows from top to bottom. There is another type of API, and that is the functional API. And that is really, really powerful if you've got like multiple inputs, multiple outputs, multiple connections. You need to do a whole bunch of fancy stuff with deep learning models. So I've definitely got one of those coming up for you. A little bit more advanced, but we do have that coming up. So sequential is great if you need something quick and easy. And that's what we're going to be doing in this case for deep learning classification. Then the next thing that we're bringing in are a whole bunch of layers. So the layers that we've brought in are available through from tensorflow.keras.layers import conv2d. So this is a convolutional neural network layer. So if we actually type in conv2d into Google, and we don't want the PyTorch equivalent, we want the TensorFlow equivalent. So this is a 2D convolutional layer, e.g. spatial convolution over images, which is exactly what we're doing. So we're bringing in our convolutional 2D or conv2D layer, a max pooling layer, which effectively acts as a think of it like a condensing layer. So it actually goes through your images and actually condenses it down. So it goes, what's the max value in this region? Only return that region. So rather than returning all of the data from our convolution, we actually condense it down. Then we're bringing in dense. So this is a fully connected layer available through Keras. We'll also bring in the flatten layer. So this is what allows us to go for my convolutional layer, which has channels or kernels, namely channels, and it actually reduces it back into a format which our dense layer will be able to take so that we can only get one output at the end. And then we've got dropout, which is typically used for regularization, but I don't think we actually use that in this. But anyway, we've got a whole bunch of layers. So typically when you're building neural networks, you're going to form an architecture, and an architecture is a whole bunch of different layers or hidden layers which form a deep neural network. So in order to do that, first up, we are going to create, or let's actually go and import that. First up, we are going to create a model, and we're establishing that as so. So model equals sequential. Now, I'm going to show you the way that I typically do this, but you can always pass through the layers inside of the sequential class. So I could actually do conv2D here, and then add in all the stuff, and then just sort of stack these as so. But I typically use the add method and actually sort of chain them on when I'm using the sequential API. But you'll see people do it like that as well. So that's just the thing to call out. If you see people using the sequential API like that, perfectly fine. This is just a matter of choice. So we are establishing our sequential class, or an instance of our sequential class. So we've written model equals sequential and a set of parentheses. Now we're going to add in our layers. This is where the magic happens. So we have, let me break this out. We're not actually using dropout. We could actually get rid of that. Would still work over here. So we've got 3 convolution blocks. We have a flatten layer, and we've got 2 dense layers. So let's break this up. So this first section over here is performing or adding a convolutional layer and a max pooling layer. So model.add, and remember how I said that you can either stack them or pass them direct to the sequential class, or you can use model.add to add layers. Now I'm adding this sequentially. So this means that the first layer in my deep neural network is first up going to be an input. So whenever you're passing through a first layer, that first layer needs to have an input, or either needs to be an input layer. Now, again, I'll talk about that more when we do functional models later on, but know that our first layer is a convolution here. So model.add, and we're adding a convolution, and this convolution is going to have 16 filters. That is what a convolution has. So it's got a whole bunch of filters, and it basically scans over an image and tries to condense or extract the relevant information inside of that image to make an output classification. So we've got 16 filters, and our filter is going to be 3 pixels by 3 pixels in size. And we are going to have a stride of 1. This means that it's going to move 1 pixel each time. So it's going to go bang, 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 so on and so forth. Now you can increase that stride. You can increase the number of filters. You can increase the size of the filters. These are all what we call architectural decisions. Now, you might have actual state-of-the-art models which actually prescribe how you do this. So if you actually go and take a look at how ImageNet does classification, there is a specific architecture that is used there. How we actually go and change these particular hyperparameters or these particular model parameters influences what our model performs like. But typically when you're doing convolution, you have the number of filters, the size of the filter, and the stride. Another really important function or another aspect of it is the activation that gets applied. So here we are applying a ReLU activation. So let me show you this, a ReLU activation. Really all we're saying is that we're taking the output from this convolutional layer and we're going to pass it through a function that looks like this. So that means that any output that was previously below 0 is now going to be converted to 0, and we are going to preserve the positive values. So this effectively means that we are converting any negative values to 0, and anything that's positive remains unchanged. This allows us to take into account a non-linear patterns, right? So if you've got no activations and really all you're building is a deep neural network, which is linear in nature, so it's not necessarily that powerful. This is where the power comes from, applying all these activations. There are a ton of them, right? So another popular one that we'll use as well is a sigmoid activation. And that looks like this. Now, these can sound really complex, but just think about it as that we're taking all of our data or all of the output from a layer and we're passing it through this function to modify what the output looks like, right? So we might have a whole bunch of numbers between I don't know, negative infinity and positive infinity, or like really, really small or really, really big values. But by going and actually changing it and passing it through one of these activations, we're reshaping what that output looks like, right? And we're reshaping what the function looks like as a result of that as well. Cool. So what's the full line? I've gone through and talked about this a ton, but so we're going to read a model.add conf2d. So we're going to have 16 filters of shape 3x3. And then we are going to have a stride of 1 and a pass through a ReLU activation. We are also going to specify what our input shape looks like. Now, remember that I said that the Keras image dataset from directory function actually reshapes our images. Well, our images are going to be in the shape 256 pixels by 256 pixels by 3 channels. So they're going to be 256 pixels high by 256 pixels wide by 3 channels deep. And again, we pass this through into our we just pass it through in our first layer here. Then we're applying a max pooling layer. So this is just going to take the maximum value after the ReLU activation, and it's going to return back that value. So it's going to scan across and go, it's effectively going to condense the information. It's not just going to take one number. It's actually going to do it over a set region. So what is this? Let's actually take a look. What's the default? Max pooling 2D, question mark, question mark. So it's going to go over a 2x2 region. So you can see 2x2, 2x2, and it's going to take the max value out of that 2x2 region. So it's effectively going to reduce our image data, I think by half in that particular case. So rather than having, half based on the rows, or half based on the rows, half based on the width as well. So it's going to condense that information down. And then we've effectively got another one of those blocks over here. So again, the next set of layers that we're adding, so model.add conf2d. So we've now got 32 filters of shape 3x3 of stride 1. And again, we've got a ReLU activation, another max pooling layer. So then we've got another convolution block. And then we've got exactly the same over here. This time we've just got 16 filters. And then what we're doing is we're actually flattening this data down. So when we actually apply a convolutional layer, the filters are going to be the last channel. So we're going to condense the rows and the width, and then the number of filters will form the channel value. Now, when we actually go and pass this to our dense layer, we don't want that channel value, right? Because we want to condense it down to a single value. So by flattening it, that's what we're effectively doing. So then we're now going to have 256 values as our output, and then finally 1 value as our output here. So if we actually go and run this, let's actually talk about this in a little bit more detail. So we've gone and flattened it. Then the last 2 layers that we apply are dense layers. So these are fully connected layers. So if you've ever seen a neural network and you see a lot of little dots and they're all connected and they go down to a point, these are referred to as fully connected layers. So inside of Keras, we call them dense layers. So we've got dense, we have 256 neurons. And again, we're applying ReLU activations here. And then our final layer is a single dense layer. This means that we're going to get a single output. And that output is effectively going to represent 0 or 1 because we have a sigmoid activation. So if we take a look at what our sigmoid activation does, let's zoom in. Our sigmoid activation takes any output and converts it into effectively a range between 0 and 1. Now, our 0 and 1 map to our happy and sad classes. So if it is 0, that is, I can't even remember what it is now. So if it's 0, it's going to be a happy person. And if it's 1, it's going to be a sad person. That is what our final layer is going to output there. So you can see that there. Cool, right? And that is our deep neural network. So if we go and run that layer, that is successfully run. The next thing that we need to do is compile that. So this is the next most important bit in your neural network. So we type in model.compile, and then remember our model was initially initialized up here. And then to that, we pass through a few things. We pass through the optimizer that we want to use. And in this case, we're going to be using the Atom optimizer. There are a ton of optimizers. So if we type in tf.keras, actually, is it tf.optimizers. There are a ton. So we've got Ada Delta, Ada Grad, Atom, Atom Max, FTRL, I haven't seen that one too much, NAtom, RMS Prop, SGD. So again, there's a ton of optimizers that are actually available. So in this case, we're going to be using the Atom optimizer. Then we're specifying what our loss is. And our loss in this particular case, because we are performing effectively a binary classification problem, it's going to be tf.losses.binary cross entropy. And the metric that we want to track is accuracy. You can pass through a bunch more in this particular case, but our accuracy is going to tell us how well our model is classifying as either 0 or 1. So if we go and compile it, this is my favorite bit. So by typing in model.summary, you can actually see how our model transforms our data. So remember, our model takes in an input of shape 256 by 256 by 3, right? 256 by 256 by 3. Our first convolution layer converts it to be 254 by 254 by the number of filters. So that 16 is coming from up here. Then we apply a max pooling layer. So it converts it from 254 by 16 to 127 by 127 by 16. That 127, remember how I said because it is shape 2, 2, it's taking 254 divided by 2, which gives us 127. So it effectively halves the output that we're getting out of this convolutional layer there. But it is not a trainable layer, right? So you can see that there's no parameters assigned to it. So it shouldn't effectively increase the size of our model too much. It just condenses stuff down. Then we're going and applying another convolution layer. So again, this one's going to 125 by 125 by 32. Now we could actually preserve the size from over here by applying some padding, but I'm not going to delve into that for now. So we're going 125 by 125 by 2. And again, we've got 32 filters. That is coming from over here. And then we are applying max pooling again. So it's going to be halving our data. Then we've got our last convolution block, 60 by 60 by 16. We're applying convolutions, 30 by 30 by 16. And then we're getting our flatten layer, right? So we've got 14,400 values. Let me enable scrolling so I can show you this. So what we're doing is we're taking the outputs from this max pooling layer and we're converting it into a single dimension. So if we type in, 30 by 30 by 16, that is the number of outputs which are passed to our flatten layer. So you can see that we're getting all of these dimensions or all of these elements here. That multiplied by that gives us the number of inputs that are going into our flatten layer. So we're condensing them down into a single dimension. So rather than having a multi-dimension or multi-rank tensor, we're converting it down to that. Then we pass it to our dense layer, which is 256, neurons, which is over here. And then we finally go down to a single layer over here, or a single output layer. Cool. Now, if you're probably wondering why this is 257 parameters, keep in mind there's a bias term as well, right? So it's going to be the value, the weights from your neurons plus the bias term. That gives us our total number of parameters. So 3,696,625 values. So it's pretty, it's not monstrous, right? You've probably seen like BERT or Big BERT, like those are massive models, GPT-3, huge. Ours is 3.7 million. Now we could probably condense that down as well if we really wanted to, but in that particular case, that is our deep neural network now modeled. So we can get rid of this, get rid of that. That is our neural network. That is step 3.1 now done. So we've now gone and built our deep learning model, right? And so we've taken a look at our imports. We've taken a look at some of the different types of layers that we'll use. And we've also seen how we can stack these layers up. Now, the next thing that we want to do is actually go on ahead and train. So first thing, we're going to create a log directory. And we've already got this created. So you can see over here, I've got a folder called logs. So we are just going to create a variable which points to that. And then we're going to create a callback. So these callbacks are really, really useful if you wanted to save your model at a particular checkpoint, if you wanted to do some specific logging, which is what we're going to do. Now, in order to do this, we're creating a callback. So tensorboard_callback, and we're setting that equal to tf.keras.callbacks.tensorboard. And we're specifying the log directory equal to this logs folder over here. So when you go and do this, you're going to have your TensorBoard logs logged out. I'm going to talk about this more in a future tutorial, but we're setting it up now. So TensorBoard_callback, and we're passing through this parameter here. So this is going to log out your model training as it's training. So if you wanted to come back and see how your model performed, did it vary at a particular point in time? Do we need to drop our learning rate? You're actually going to see that inside of these boards, but we can actually just plot them using the history that you collect from your training step, which I'll show you in a sec. Cool. So that's our callback established. Now we're going to go on ahead and fit our model. So there's two really, really important methods when it comes to building a neural network: model.fit and model.predict. So fit is the training component. Predict is when we actually go and make predictions. So model.fit is going to take in our training data. And remember, our training data was 4 batches of 32 images each. Our epochs is how long we're actually going to go on ahead and train for. And one epoch is one run over our entire training set of data. We're also going to pass through our validation data. So this means that after we've gone and performed gone and trained on all of our training data or training batches, we're then going to run evaluation on our validation data. So we can actually see how well our model is performing in real time. then we're also going to pass through our callbacks. So if we wanted to go and apply additional callbacks, or let me know if you want a tutorial on callbacks, guys, I'm more than happy to do it. So here we're actually specifying that we want to log out all of the information from our model to TensorBoard, so we could open it up inside a TensorBoard later on. And by storing it inside of a variable called hist or history, we're going to be able to take out all of the training information from our training data and our validation data and plot them out inside of step 3.3. So if we actually go and run this now, this is going to kick off our training run. So let's run it. And you'll actually see our deep learning model start training. So it might take a little while to start, but eventually you'll start to see it training. So it's going really, really fast because we've obviously got a GPU, but that is now training. So you can see it's taking 377 milliseconds per step. Our loss is going down. So ideally you want to see your loss go down and your accuracy go up. And so what you've got over here, so this is the loss on your training data. This is your training. Let me zoom in because you probably can't see that. This is the loss on your training data. This is the accuracy for your training data. This is your validation loss. And this is your validation accuracy. So ideally you want to see them, or you want to see your losses decrease both pretty consistently and pretty steadily. And you want to see your accuracies go up pretty steadily as well. So over here, so you can see it's definitely performing way better. So look, our losses dropped down significantly and our accuracy has got up to 100%. So again, it's performing really, really well by the end. And that was it. So it went really, really quickly. That's how deep neural network trained, guys. That's how quick it goes. So this is obviously with a GPU, so it's a lot faster. Without a GPU, I think we saw roughly a double increase in the training time. So again, you'll still be able to do this without a GPU. But that is our deep neural network now trained. The magic is done. Now, cool thing is because we've gone and saved it inside of, or saved our training history inside of a variable called history, we can actually get a whole bunch of information from this. So if I show you hist, this shows us our callback. So if I type in hist.history, there is a whole bunch of information available in here. Let me scroll. So you can see that we've got our loss information. We've got our accuracy information. So that's on our training data. We've also got our validation loss information. And we should also have our validation accuracy information, which you can see there. Pretty cool, right? But we can actually plot this performance out, which is what I've got here. So here I'm just using matplotlib, so plot.plot, and we're grabbing our training loss and we're grabbing our validation loss and we're plotting those. So here what you're going to see is that our training loss has the color teal and our validation loss has the color orange. Let's go and plot it out. So you can see that our loss has sort of decreased pretty steadily over time. We've had one bit of a spike there, but it's sort of come back. If you start to see your loss going down and your validation loss sort of rising up, that is an indication that your model may be overfitting. So it might be time to look at applying some regularization. Might also mean that we need to apply some data or change some data. If you don't see these decreasing at all, or if you see your green line like not decreasing or going weird, this might mean that you need to take a look at your training data again, maybe potentially consider a larger neural network or a more sophisticated neural network, because that means that it's not able to learn or reduce the loss for that particular data or that training data overall. So it might mean we have a bit of a bias problem. Okay, so if the validation loss starts tearing off, that might mean you have a variance problem. So again, regularization is your friend in that particular case. Okay, so we've got our loss metrics, so visualize those. Now we can also take a look at our accuracy metrics. So again, this sort of little block here is pretty useful because you can actually visualize just about anything that you want. And it's really, really useful when you're doing deep learning as well, because if you added more metrics, so let me go scroll up. If we added in more metrics when we're compiling our model, you'd actually be able to visualize all of them. So in the iris tracking video that I'm working on as well, I actually show how to do that for a whole bunch of metrics. Okay, so that is our loss visualized. Now we can also visualize our accuracy. So again, we're using matplotlib to visualize these. So if we go and run this one, you can see our accuracy steadily increased over time. We had a little bit of a pop out there, but again, we've come back and it has resolved back up to 100% accuracy, which is very, very good, right? Obviously, this model is performing well. There's not a ton of data. So ideally, you'd want to flesh this out with a ton more data. But in that particular case, that is our model now trained. So we've actually gone and completed our modeling step. So we've gone and built our deep learning model and we've used this sequential API. We've gone and trained our model using the model.fit function. And I've also shown you how to pass through your training data, your validation data, as well as setting up a callback. And we've also gone and taken a look at our training performance. So we've visualized our loss and we've also visualized our accuracy. Let's jump back on over to our client and we might be onto our evaluation step.
So we've finished training our model. Now it's time to test it out. Of course. Wait, what does that mean? Well, think of how you might test an athlete. You put the athlete through its paces and review certain metrics. So you might measure a sprinter by their 100-meter dash time. For our classification model, we'll do the same. Ah, got it. So we're gonna check how fast our model is. Not quite. We've got a few different metrics we'll use for classification. These include precision, recall, and accuracy. Let's jump to it.
So we're in the end game now. Evaluating performance. So we've gone and trained our model. The next thing that we want to do is actually go and evaluate performance on our testing data. Because remember, we held out that partition that our model has never seen before. So there's two things we want to do. First up, evaluate it, and then we'll also grab some random images and test that out. So in order to evaluate, we're going to import a couple of key metrics. So from tensorflow.keras.metrics, import precision, recall, and binary accuracy. These are different measures that you typically use for classification problems. So I'm going to import those. And then what we can do, or in order to use them, we need to establish instances of them. And then what we can do is update our state as we actually go and make predictions. So we can go and instantiate those. So I've written pre, and these are pretty crappy variable names. I think I was running out of energy. So pre equals precision. And again, we're grabbing this class over here, creating it. Re equals recall. And then accuracy equals binary accuracy. Then in order to go and test them out, we're going to loop through each batch in our testing data, which I think we only had one batch anyway, right? So len test, nope, lowercase. One batch anyway. So for batch in test.asNumPy iterator, so that's going to bring back our batch, and then we can unpack it. So x comma y equals batch. So this is going to be our set of images. This is effectively our y true value. Then we're passing through our image data to our model. So model.predict is how we make predictions. And that is going to return back a set of values between 0 and 1, because remember, we've gone and passed it through a sigmoid activation. So in order to update our metrics, we can then type in or use the update state method. So precision.update state, and we pass through our y true value and our predicted value. Oh, I've gone and screwed that up. So we pass through our y true value and our y hat value. So you can see those there. And we've gone and done that for precision, for recall, and for accuracy. So we'll then be able to see how it's actually performed on our test data. So if I go and run that, should run for a little sec, and then we can actually print out those results. So let's actually make this a little bit easier to read. So f equals precision.result. So this is precision, RECI. And I think we can write .numpy as well. And what is this? So this is recall .numpy. And this is accuracy. My head blocking that off? Nope. Okay. .numpy. What have we done? We haven't finished it. Got to close that. Boom. Okay. Should close that over there. All right, so there we go. So we've now gone and printed out our performance on each of those different metrics. Our precision is 1, so a higher precision means your model is performing better. Our recall is 1. Again, high value on recall means you're performing better. And our accuracy is 1. So again, high value means you're performing better. Now, each of these metrics are between 0 and 1. So this is the highest possible value it can take. Now, again, if you want a deep dive on how these metrics are calculated, or let's say, for example, wanted to do a confusion matrix, let me know and I can delve into those. But just know that this model is performing pretty much as well as it can on a single batch of data, and considering how little data we've actually given it to perform. So we've got a precision of 100%, a recall of 100%, and an accuracy of 100% as well. Now, normally I don't like to leave it there. I like to actually go and test it out on data that's outside of that batch. So let's actually go on ahead and do this. Now, the first import that we're going to import is CV2, but I thought we've already imported OpenCV. We should have. We imported it when we were doing the HC. Yeah, we've already got that. So we can actually skip that. We don't need to import OpenCV, but for now, let's just import it anyway. I'm wasting time. What we're going to do is we're going to read in an image that our model has never seen before. So what we're going to do is let's go and grab a random image. So let's actually go to page 2 or scroll further down. Let's grab this dude. So I'm going to save this image and I'm going to save it into our image classification folder. We're going to call this sad test. And it saved it as JFIF. I don't know why Google does that. It's so frustrating. Sad test.jpg. Yes, okay, cool. Then we're going to get an image of a happy person. Happy peoples. Find a happy dude. And so this is completely out of sample, right? Our model's never seen this before. Let's go. This one's great. All right, let's save this image. So happy. That's WebP. That's not going to work. So again, it needs to be .jpg. It's just going to make your life a whole bunch easier. Let's grab this one. Happy test.jpg. Okay, cool. So we've got 2 test images. So if I open up my folders, so you can see, why are they not there? There we go. So we've got happy test.jpg. So this is that girl is super happy, and we've got a sad test. Got this dude, dark and stormy, is ready to drop a beat. All right, now what we're going to do is we are going to read in that image using cv2.imread. And so first up, let's read in our happy image. So we can type in happy test.jpg. So that should read in our image and we should plot it out, right? Now remember, this OpenCV is going to read it in as BGR rather than RGB. Do we fix that here? No, we don't. Let me show you how to do it. CV2 to CVT color. And then we're going to go and pass through the color conversion code, cv2.color_BGR to RGB. And that should visualize it in its correct color. So there you go. So we've gone and fixed up the color there. It's gone and successfully loaded it. Now, remember when we pass through our data to our neural network, it needs to be in the shape 256 by 256 by 3. So 256 pixels high, 256 pixels wide, and it needs to be 3 channels. So what we can actually do is use tf.image.resize to resize our image before we pass it through to our neural network. So if we actually go and run this, that is what our image looks like now resized. Now again, we could go and apply the cv2.cvt color method over here and grab this, paste it here. And we are throwing an error. That is because it is an integer. Run that. Doesn't look like it's playing nicely. Anyway, we've gone and transformed it now. So with TensorFlow. So you can see that we've definitely gone and resized it just because we've read it in using OpenCV. We're getting that weird coloring. But let's actually go and test this out now. So if we actually go and pass this through to our model, so model.predict, and then we're passing it through to our neural network. So now, quick word on how we're actually doing this prediction. Our neural network expects us to pass through a batch of images, not a single image. So what we actually need to do is we need to encapsulate it inside of another set of parentheses or arrays, or put it inside of a list. So in order to do this, and you'll see this done quite a fair bit, is we can type in np.expanddims, pass through our image, which is right now called resize, because we've gone and resized it using tf.image.resize. Pass that into there. And if I type in what axis I want to apply the extra dimension, you can see that right now it's just stored inside of an extra dimension. So let me show you the first value. Oh, you can see that we've got a whole bunch of extra dimensions there. This is the first value. Let's scroll it. So you can see that we don't have an extra set of parentheses there. By throwing it in there, literally all we're doing is we're encapsulating it in another set of arrays, or putting it inside of another list. So if I actually show you the shape now, dot shape, it's 1 by 256 by 256 by 3. If we take a look at the shape for this, it's 256 by 256 by 3. So we're literally just wrapping it in another set of arrays. Now, what we're also doing at the same time is we're dividing about 255 to scale it. So if we go and run this, take a look at y hat, so 0.28. So remember, what was a sad or a happy person? Happy person was 0, which you can see there. So happy is 0, sad is 1. So in this particular case, our model has successfully predicted that this particular person is happy. Now, the reason that we're making this assumption is if a particular, in our binary classification problem, what we're saying is that 50% is our cutoff point. So if it's below 50%, we round down to 0. Then this particular case, we're saying that our person is going to be happy. So it's successfully classified that particular person. We've got y hat twice there. We don't need that. Now, the way that you can extrapolate this, or actually explain this in regular terms, is that our predicted class is happy if it is less than 0.5. So if y hat is greater than 0.5, the predicted class is going to be sad. Otherwise, the predicted class is going to be happy, which is exactly what we've said over there. So because it's 0.28, it is less than 0.5, which means that our model has successfully predicted it as happy. Pretty nuts, right? Like we didn't have a ton of data. We didn't even train for that long. And we've successfully gone and built a deep neural network that performs classification. But let's actually go and test it out on our sad person as well. So in order to do that, we just need to pass through a different image. So this one's going to be sad test. And if we go and run this, so our model has gone and given us a probability of 86.8%, which means it's going to be above 50%, which means we have predicted sad successfully. Take a look at that. Predicted class is sad. So really quickly, we've gone and been able to perform or build a deep neural network that is able to perform sentiment classification using nothing but a couple of images we've collected from the web. Let's go jump back on over to our client and give him one last final update.
All right, home run, baby. You know it. The last thing we need to do is save our model so we can reload it at a future date. So this means another developer or engineer could use the model, right? Right, this could also be deployed as an API or to an edge device. Let's finish this.
Alrighty, we're at the final step. So saving the model. So this is a really important step. So you've gone through all to this amount of effort. The last thing that you want to do is save this model so you can go and use it again if you did want to. Now this is relatively straightforward. We can import or bring in the dependency from TensorFlow called load model. So from tensorflow.keras.models, import load model. So then what we can do is actually use this load model function to be able to load up our model. Now, first up, what we actually need to do is save the model. And to do that, we can just use model.save. Now we're going to save it inside of the folder models and we can name it just about whatever we want. So we could call it happy sad model. And because we're saving it as a H5 model, what we're actually doing is something called serialization. So we're taking our model and we're serializing it onto something that we can store as a disk. So this is similar to what you might do when you zip a data set, when you go and RAR a data set. H5 is a serialization file format. So it basically means that you're going to have a file called happysadmodel.h5, and then we can reload that using the load model function up here. So the full line is model.save, and then to that we're passing os.path.join, and we're going to be saving it inside of our models folder, which I've already got created over here. Nothing in there at the moment. And we're going to be saving it as happysadmodel.h5. It could be whatever you want it to save it as, right? If I go and run that inside of our models folder, you can see we've now got our happysadmodel.h5 file over there. So we're looking good. Now, the next thing that we want to do is actually go and reload this model. So let's actually go and rename it. So we're going to call it new_model, and we can use load_model to load that model back up. Now we need to pass through the full file path to our saved model in order to reload it. So we can actually grab this H5 file name here, pass it over to here. So we are basically saying it's going to be inside of the models folder. So models and then happysadmodel.h5. So we're basically going to give it this file path to the load model function to be able to load it back up. So if we go and run this now, this is our new model. So new model is our sequential Keras model. And if we go and pass data to it, so again, we're going to pass through our resized image. So np.expandIms, passing through our resized image, which we're scaling, and we should get a prediction. Again, you can see we're getting a sad prediction. So if we go and run this again, so let's call this y hat new. Grab this block over here. So what we're going to say, if y hat new is greater than 0.5, you can see still predicting sad. That in a nutshell is how to build a deep neural network for image classification. So we've gone through a ton of stuff in this tutorial. Let's quickly recap. So we first up went up and set up our image or our environment to be able to set up and load our data. So we went and imported a bunch of dependencies. We went and removed some dodgy images, and we went and downloaded them originally from Google. Now remember, you can get that image extension, which makes your life a whole bunch easier. So what was it called? Download all images. It's just a Google Chrome extension, nothing fancy there. It just makes your life a ton easier when getting images. We then went and loaded our data set using the image data set from directory method. We went and pre-processed our data, so we scaled it and we split it. We then went and built our deep neural network, and we went into a bit of detail as to how we've actually constructed this architecture. We then went and trained it using model.fit, took a look at our performance over time. We went and then finally evaluated it over some new images that we've got off the web. And last but not least, we've gone and saved our model down to our disk so we can bring it back when we need to. That, in a nutshell, is this tutorial done. Thanks again for tuning in, guys. Peace.
Thanks so much for tuning in, guys. Hopefully you enjoyed this video. If you did, be sure to give it a big thumbs up, hit subscribe, and tick that bell, and let me know what deep neural network type tutorials we should be doing next. Did you enjoy this one? Did you build it yourself? And what do you go on about and classify? Thanks again for tuning in. Peace.